Good day, I'm Dr. T and welcome to my office. Today I'd like to talk a little bit about hydrates. So some compounds, when they become a solid, they'll crystallize and in the process will incorporate waters within the crystals. To say the waters are simply trapped in the crystal is definitely a bit of an oversimplification, but it is a useful way of thinking of things. Now, with these compounds, we call them hydrates. We say that they've been hydrated. Think like drinking a bunch of water on a run, that kind of hydrated. Because they, once again, have water trapped within their crystals. Now, the amount of water tends to be fairly fixed. They have a kind of a preferred amount. Obviously, this is one that can change, so you can have less water in there if there's just isn't enough. Generally speaking, they're not going to want to have too much more. In that case, you're really just dissolving your crystal. But with these hydrates, they're not dissolved. It's actually storing water as part of the crystal. So to look at these, we've got a couple of ways of thinking about them. For starters, we can write a chemical formula. And this is actually going to be fairly important for us. So when we're weighing out a hydrate, we need to know what the formula weight is, and that formula weight will include the waters of hydration. However many waters are crystallized with the thing. The way we write the formulas is fairly straightforward. We write the formula for the compound in question, such as CoCl2. Then we place a dot. The dot means a complex. It means that it is associated with, but it is not really a part of the compound. And then we write the number of waters that we have, like 6H2O. Yay, we have ourselves a formula. Obviously, if there's only 2 waters in that particular formula, then you would put a 2. If there's no waters, what we call anhydrous, then you wouldn't put anything there. You just write the chemical formula like normal. Now, when we're naming them, we're going to name them basically in the same fashion. So we would name it normally, so cobalt 2 chloride, and then we would give it, in Greek, the number of waters. Say hexa, and then say hydrate. So, the current example would be cobalt 2 chloride hexahydrate. Yay! Now, if you wish to indicate that your compound is in its anhydrous state, it doesn't have any waters, then you can tag the word anhydrous in front of it. So I could say anhydrous cobalt 2 chloride. This is helpful, of course, if I want to do that. I don't typically do this for compounds that don't form hydrates because it's kind of redundant. Anhydrous steel. Yeah, we know there's no water inside of your steel. The amount of water trapped within the crystal is not necessarily fixed and is actually relatively easily changed in many compounds. For a good many, we can drive off the water and convert a hydrate to an anhydrous compound simply by heating the compound, usually around the boiling point of water, although it does depend on the compound. Now, not all compounds will do this. Some of them tend to degrade or form other weird chemistry when heated, so this isn't really an option. But for a good many of our hydrates, we can convert them to anhydrous by simply heating. Now, some hydrates will actually convert themselves to either a lower number of hydrates, so, maybe like a decahydrate down to a monohydrate, or all the way to anhydrous, simply with room temperature and reasonably dry air. Probably mispronouncing this, but this is known as aerofluorescence. Not probably, I'm quite certain I just mispronounced it. I'll have the word popping somewhere. Okay, now, a much more common property is actually to go in reverse. An anhydrous compound becoming a hydrate. And this is known as being hydroscopic. This is the ability to pull water from the atmosphere and incorporate it into the crystal. This is actually quite useful for what we call desiccants. Desiccants are compounds that pull water from the atmosphere and thus can make the air nice and dry. Yay! Now, some of those compounds not only can pull water out of the atmosphere to go from the anhydrous to the hydrate, once they're a hydrate, they'll actually continue pulling water from the atmosphere and can actually make themselves into a concentrated solution. This is called deliquescence. Once again, I will put the name somewhere over here because I'm butchering the pronunciation. These compounds, of course, are always somewhat inconvenient to work with because if you leave the lid off, you have soup. So with that said, have a wonderful day.